Hello everyone and welcome back. Today we'll be looking into the famous cats and dogs dataset from Kaggle, and it's an extremely varied dataset consisting of 25,000 images of cats and dogs, often with the subject somewhat obscured, for example if they are held by a human. So let's see what this is all about, and we'll be using GPU at about 3 minutes per epoch. For 20 epochs, that equates to about 1 hour of training time, right? So let's get started. And as you can see in the figure 3-17, there are some unusual dogs and cats images. Like in the first one, you can see there's a dog having ears like a cat. Then there is a dog sitting with a human. And in the last image, you can see a cat who is licking her own paws, and looks like the third one is pretty funny, having glasses on. So let's see how we can build a classifier that would actually classify between cats and dogs. The cat is the lower right corner with its eyes closed, eyes down, and tongue out while washing its paw gave the result in figure 3-18. So the last cat we entered in a classifying, and it gave an output that it's a cat. So we can see the network that we are going to train is kind of almost certain that it was a cat. And you can find the code to this in a GitHub repository. I've already put it there, and it's with the name it's in the name dogs versus cats transfer learning classifier. So multi-class classification we'll be looking into next, where what kind of thing is we gonna do is we are gonna use a classification problem here only, but this time we will be classifying 3 categories rather than 2. So we are here using a data set that is rock, paper and scissors data set. And what kind of differences we'll see here is the important part. So as I have already highlighted, instead of a single neuron that is a sigmoid activated or 2 neurons that are binary activated, our output layer will now require n neurons, where n is the number of classes you want to classify. So as I was told you before that now we'll be classifying more than 2 classes. That's why we'll not be using a binary activated neuron. Also, you'll have to change your loss function to an appropriate one for multiple category, because right now we are using binary classifiers for classifying into 2 categories, but now since we have 3 categories of rock, paper and scissor, we'll be using a categorical cross entropy that can classify multiple classes. If you're using the image data generator to provide your images, the labeling is done manually. So multiple categories will work the same as binary ones. So we don't have to take care of the subdirectories and anything, because image data generator will simply take care of that and label the data. Consider, for example, the game rock, paper, scissors. If you wanted to train a dataset to recognize the different hand gestures, you need to handle 3 categories, right? Fortunately, there's a simple dataset you can use for this. So there are 2 downloads, a training set of many diverse hands with different sizes, shapes, colors and details such as nail polish, and a testing set of equally diverse hands, none of which are in the training set. So there are 2 downloadables. So one is our training set and one is our testing set. We'll see it when we are actually writing the code. So here in the image you can see the first image is of a rock, the second image is of a paper, and the third image is of a scissors. Download and unzip the dataset. The sorted subdirectories are already present in the zip file. So it's nothing different. First, you can already see here is the data set. This all is the data set here. Then you are simply unzipping it. You can just find the local zip directory where the data set is located. You are reading the data set. You are extracting all in a temporary folder. Then you're closing it. Finally, your training directory, you give the path for training directory. Then you store the training data generated in a using image data generator. So all the image augmentation like rescaling and rotation and height width adjustments, zooming, sharing, flipping, all goes here. And finally, we just store our training data here. We get our training data here. So whenever we are calling our training data, we'll be calling train generator, right? So what's happening here is train generator equals training underscore data gen. That was the place where we were actually calling our training data. Dot flow from directory, that is directory. We're defining a directory here, that is training directory. The target size is 150, 150, and the class mode is categorical because there are more than 2 categories. However, that when you set up the data generator from this, you have to specify that the class mode is categorical in order for the image data generator to use more than 2 subdirectories. When defining your model, while keeping an eye on the input and output layers, you want to ensure that the input matches the shape of the data and the output matches the number of classes. That is 3 now. So what it's actually saying here is that we need to match our input shape like 150, 150, and we have to also take in account the number of classes on the output because the classes will change depending upon the results we want. So here the model, we are defining a model.sequential as before we have already done in chapter 1. Then the first convolutional layer having input shape, we are defining the input shape here actually 150, 150, 3 with activation as relu. Then max pooling layer, and again we are just going ahead and continuously adding more convolutions and pooling layer. So after fourth convolution layer and max pooling layer, we'll be adding a flatten layer to flatten down the results. And finally we add two dense layers as the neural hidden layer, and that is all. When the last dense layer is added, so we add 3 there because in the output we have 3 classes, that is rock, paper and scissor. That's why in the last line we add 3 neurons in the last dense layer with activation as softmax. Finally, when compiling your model, you want to ensure that it uses categorical loss function such as categorical cross entropy. So it says binary cross entropy will not work on more than 2 classes. So when we compile the model, we are using categorical cross entropy, optimizer for RMS prop, and metrics for accuracy. Then as similar as before, we are using history equals model.fit with the train generator where all the training data comes in, and epochs 25, and validation data where validation data comes in, and verb is equal to 1. Your code for testing predictions will also need to change somewhat. So when we are testing predictions, the last code that we always write for testing is also going to change somehow, because now there are 3 output neurons and they will output a value that is close to 1. So what is going to happen is the values would be 3, but the sum will be always equal to 1 because of softmax. So as we have read before in chapter 1 that we always get a probability, and we all know that the sum of all the numbers cannot be greater than 1 in probability. Note that when using image data generator, the classes are loaded in alphabetical order. So while you might expect the output neurons to be in order of the name of the game, the order in fact will be paper, rock and scissors. So let's try this last code. What it says is just to upload the files from your desktop or wherever you are uploading from to the training for to the testing type. So import numpy is np, and importing files, that is the usual function to upload files in Google Colab. Just calling that and calling importing image. So we are using uploaded equals files dot upload. That's a function. So we are checking in the uploaded dot keys if the function, if the path equals function predicting images, that's the image that's incoming. We are getting the image size, that is 150 by 150, because we have to give the image input like 150 comma 150 comma 3 for the three channels, but the image coming that we are uploading for testing is not of that sort. So we are actually converting that image to array and then also expanding the dimension so that it matches to the input size of our convolution neural network. And finally, the image, we stack the image, and finally we use model.predict on images that we have entered, and finally we write down the classes. So you can see the kind of output you get. So here is the output. You can see in the image itself under paper1.png, you can see that the output comes to be 1.0.0. So what does it say? That it is positive for paper and it's 00 for rock and scissors. So that means the image was of a paper only. Then there is some data available in the download one. You can always, I link that in the video description, and you can just check it out and use it for the testing purpose. Now there is one more thing that comes quite handy to overcome overfitting. So earlier in this chapter, we discussed overfitting, where the network may become too specialized in a particular type of input data and fare poorly on others. So one technique that helps to overcome this is a dropout regularization. When neural network is being trained, each individual neuron will have an effect on neurons in subsequent layers. Over time, particularly in large networks, some neurons can become overspecialized, and that feeds downstream, potentially causing the network as a whole to become overspecialized. So what's happening here is that in a neural network, when it's training, there might be some neurons or individual neurons who have a much larger effect than the next or the others neuron, right? So there might be one or many neurons, subsequent neurons, not in one layer but in different layers. There might be neurons that have more effect than the rest of the neurons. So over the time, as the network is growing and the model is learning or training, these neurons become over specialized. Hence our training accuracy becomes too large or almost near to 100%. So that thing happens because of over specialization of neurons, and that leads to overfitting as well, right? Additionally, neighboring neurons can end up with similar weights and biases, and if not monitored, this can lead the overall model to become over specialized to the features activated by those neurons. So that's also true, that the neuron that becomes over specialized might also affect the neighboring neurons, because they might end up having the similar and biases and weights, and if not monitored, the overall model will become over specialized. That is what we call overfitting. So for example, consider a neural network in next figure where there are layers of 2, 6, 6 and 2 neurons. Neurons in the mid layers might end up with very similar weights and biases. So it says the middle layers might end up with similar weights and biases. Let's see. So here is the figure. So in the middle there are more neurons, and they're quite neighboring, right? So there is high probability that these neurons will have more of similarity with each other in the same layer. While training, if you remove a random number of neurons and ignore them, their contribution to the neurons in the next layer is temporarily blocked. So what's the idea is actually you'll see the figure next and you'll understand it very easily what is dropout actually about. So what happens here is while you are training, it's kind of a switch. So while you're training, you kind of switch off few neurons subsequently. Like for a very limited amount of time, you shut them off temporarily and there is no data going in and out. So what happens is that these neurons can't contribute here and hence are usually blocked, but they are temporarily blocked. In the next training epoch, others, these might, the dark blue ones, these might turn on and the neighboring ones might turn off. So that is dropout regularization only. So you are actually dropping out few neurons so that they do not become over specialized or the neurons adjacent to them don't have similar weights and biases as them to become over specialized. This reduces the chances of neurons becoming over specialized. The network will still learn the same number of parameters, but it should be better at generalization. This is it should be more resilient to different inputs. So note that the concept of dropouts was proposed by Nitish Srivastava and in their paper in 2014. So this is a paper, you might just go ahead and find this paper very easily and just give it a quick read. To implement dropouts in TensorFlow, you can just use simple Keras layers. So using just this will help you add dropout to your model. So this is what dropout layer is about. So tf.keras.layers.dropout of 0.2. You just add this as you can see here in the full code. So in the model only, we're just adding the dropout layer only, and it's an example of fashion MNIST classifier. This will drop out at random the specified percentage of neurons. So 0.2 is basically 20% of neurons are dropout in specific layer. Note that it may take some experimentation to find the correct percentage for your network. Right, so training with 20 epochs gave around 94% accuracy on fashion MNIST classifier. So, but about 88.5% on the validation. This is the potential sign of overfitting because validation accuracy is less than the training accuracy. It's actually very less, to say it clearly. So what we are going to do is we've just added dropout layers in the model. So you can see 3 dropout layers have been added. When this network was trained for the same period on the same data, the accuracy on training set dropped to about 89.5%. The accuracy on validation stayed about 88.3%. These values are much closer to each other. The introduction of dropout thus not only demonstrated that overfitting was occurring, but also using dropouts can help to remove such ambiguity by ensuring that the network isn't over specializing to the training data. So now we have used dropout 0.2. We might increase percentage of dropout and we might see much better results. But since the validation accuracy and the training accuracy have come out to be near closer to each other, you can say that the overfitting has somehow been overfitting has now been not occurring. Keep in mind as you design your neural networks that great results on your training set are not always a good thing. This could be a sign of overfitting. Introducing dropouts can help you remove that problem so that you can optimize your network in other areas without that false sense of security. So what about the summary? That we have introduced to more advanced way of achieving computer vision by using convolution neural networks. You saw how to use convolutions to apply filters that can extract features from images, designed your first neural network to deal with more complex vision scenarios, than those you encountered in MNIST and fashion MNIST datasets. You also explored techniques to improve your network's accuracy and avoid overfitting, like image augmentations and dropouts. So, before exploring and going to chapter 4, you'll get an introduction. So, in chapter 4, actually, you'll get an introduction to TensorFlow datasets, a technology that makes it much easier for you to get access to data for training and testing your networks. In this chapter, you are downloading zip files and extracting images, but that's not always going to be possible. And we'll be using TensorFlow datasets from now on, so you can access lots of data and actually using a standard API. So I guess we are done with chapter 3 now. We'll start chapter 4 in the next video. But now we'll just jump to the coding area for our collab so that we can understand better how we are gonna use dropout and how we are gonna classify between paper, rock, and scissor, right? So let's just jump to Colab and see what kind of code goes into classifying rock, paper, and scissors. Now let's get started with some code. Here we'll be understanding and classifying rock, paper, and scissor with dropout regularization. Let me make it very clear that dropout regularization does not make a massive impact in this regarding this dataset, but if you are going to use some other dataset that is far more complex, it might help you. So let's see how to first get to our GPU. So all you have to do is click on runtime, go to change runtime type, go to a hardware accelerator, select GPU, and then click on save. For convenience of this video, I'm just gonna let you guys go through all this code that I've already run before, because it takes a lot of time in training the code and I've already done that for you. So let's get started. First, I'm just importing the basic imports that are required to get the training data. That was url-lib.request and zip file. Right, then this is the whole code for the zip file where I got this whole thing I got from the book only, where the actual data lies. It's actually in a zip file, so all we have to do is extract it and open it in a read format, that is R for that, and extract that all in this path. Then what are we going to do is use image data generator to get our images from that particular zip file and in a directory that's a training directory here. And the training data generator would be equal to rescale the data in or the images by 1 point by 255, that's normalization, and the rest of the things that we have already covered in image augmentation. So what we are going to do is add like bit of rotation, about 40 degrees of rotation to the images, and shifting the width, height, shear, maybe zoom in or zoom out, flip the image, and all these kinds of image augmentation techniques we'll be applying. But keep in mind that image augmentation is always applied to the training data and not to the test or the validation data. Next, we are just gonna get the train generator, and using the directory where we got our training data, we'll just set the target size of 150, 150 and the class mode to categorical. Same we'll do for the validation data, but in this case, I am just using the training data to train my model, and I have not used validation data because I had quite less time, but here it is. So here is my model. I imported TensorFlow as TF because I need to use it here. Then in my model, it's a basic sequential model with convolutional 2D layers and followed by max pooling layers. So convolution first layer has 64 neurons and has an activation of ReLU, and input shape is same as 150, 150, 3 because they are colored images. Next, max pooling layer, and the system flows on till the flattened layer, and then we have added a dropout layer in between the two dense layers. So dropout layers usually work well between two dense layers, and we don't put them deliberately into convolutional layers or between convolutional and max pooling layer or so on, because if we put dropout between convolution layers or somewhere, it might miss on some of the patterns or the features that we don't want. We want our model to learn and extract the feature information, so we don't put dropout there. But in the dense, it's only passing images and matching to the labels, so we can use dropout there. So it's about 20% of dropout. And finally, activation. Here the dense 3, as we have already read in the book, that 3 neurons for 3 classification, that is rock, paper and scissors. Finally, for the softmax activation, then we compile the model, categorical cross entropy because we need 3 categories, optimizer is RMS prop, matrix is accuracy, right? So here is something that I've used, callbacks, and we did it in chapter 1 also. And if you are willing to do this, you just do it, otherwise you may leave this whole sort of code. So what I've done here is, if the accuracy is going above 98.33%, I'm just canceling the training and stopping the training there. This was just to check whether using dropouts where my accuracy reaches 98%, because without dropouts my accuracy at the 25th epoch or around 25th and 24th epoch was around 98.33%. So I was just checking whether I get 98% of accuracy with dropout or not, and to be honest with you, I would say I got it. And here you can see that around 19th epoch I got the accuracy of 98.02%, right? So that's it. That is why I've used this callback. And if you don't feel comfortable with it, you might even leave it, because it will otherwise run for 25 epochs. That's just not too much far away from 19, right? So here is the accuracy, around 98% accuracy on the training set. So I've just finally tested it with some images. This is the same code that we've already been using. So we use files from Google Colab and we upload the images and we get the what kind of classification our model is working upon. So here I've used 3 images, paper, rock and scissor. So as you can see that paper, it has 100% accuracy that it's a paper. For rock it has 100% accuracy, it's a rock, and for scissor it also has 100% accuracy, it's a scissor. So I can say that even though I have not trained it on the validation one as and run it on the validation set as well, but it is performing quite well on the testing. But I do recommend you to work on the validation training as well. So once you have provided the training data, you have trained on that, so do test with the validation data set as well, and find the accuracy, what kind of accuracy you get, because it's kind of a measure that helps to know that whether our model is overfitting or underfitting, right? So that's it for this coding session. I hope you have learned a lot from this chapter, and it's the end of chapter 3 as well. So next we'll be going through chapter 4, and we'll be understanding a bit more about um, extracting features and what new we can learn in machine learning. And meanwhile, you can get all these data sets as well as the code from our GitHub, and I'll link the GitHub in the description below. Do check it out, and if you have any doubts or any questions, do drop them in the comment section. Thank you. I'll see you next time.